One of the fundamentals of artificial intelligence is planning. A lot of emphasis is given to deep neural networks, at least right now, because they're new and very important because they enable the robot to see the world and understand what it sees with its sensors, cameras, lidars, and so on. But what really makes robots intelligent is planning. How to get from A to B or how to execute a task in a good way. Search is fundamental to do planning. A lot of what the robot needs to do can be represented in graphs. And in order to figure out how to move through this graph or how to connect this graph in an efficient way, we use search. Basically, there's two different ways of doing search. There's the depth first search, and then there's the breadth first search. Those two searches traverse the tree or the graph in two different ways. The depth first search goes all the way from the root node to the bottom node. The breadth first tries to take every node on the same level and evaluate it in order to find its goal. When you're doing motion planning for a robot, most of the nodes has a location connected to it, so that every point or every node in the environment has maybe an X and Y position. So there's actually a cost from moving from one node to the other. Using those costs, we can compute the optimal way for the robot to traverse these nodes. That doesn't mean that it needs to traverse as few nodes as possible, but rather the cost of going from one node to another. When you add all those up, that number needs to be as small as possible. That's the optimal route. There's also different ways of finding this route. On one hand, you have the greedy search, which only looks at what's the next best step I can get. And by taking that, it gets to the goal in maybe not the optimal way, but at least it does it fast. You could kind of equate it to the gradient descent. On the other hand, you can do a full search of your environment and find the optimal path. That's often called the Dijkstra's algorithm. And you can see the duality of those two algorithms to the breadth first and the depth first search. But where the depth first and breadth first search looks at the actual points or the actual nodes in the graph, the Dijkstra's algorithm and the greedy algorithm works on the actual distance that or the actual cost that's associated with moving from one node to the other. There's an in-between, there's always an in-between, and there's a lot of algorithms that you can use for searching, but one of the most important ones is A*. A* uses a heuristic function that tells that makes a very good guess about what's the cost associated with going from one node to a goal. That doesn't necessarily need to be the right value, but it's just a good guess. In the case of X and Y, or planning in an X and Y plane, that could be the L2 norm, or the distance, the actual distance from the one point to the other. There could be obstacles in between, so you need to go a longer way, but it's a good guess. And by using that guess, we can target the search in the graph to not look at so many nodes and then find the optimal way quicker. So it's a go-between that is a bit greedy, but it finds the optimal way just like the Dijkstra's algorithm does. When you start looking into search algorithms, you find that there's actually an ocean of algorithms for specific purposes. If the graph looks in one way or the other, if there's cycles in the graph so that you actually get back to your initial position, how do you actually search a graph like that, and so on. But the basic ones are the breadth first and the depth first. And if you have cost associated, it's the Dijkstra's algorithm, the greedy algorithm, and the A* algorithm.